this section, we're going to take a deep dive into the Internet's network layer. And because there's a lot to cover here, we're going to do this in two parts. In the first part, we're going to cover the IPv4 protocol and addressing. Now, obviously, IP is incredibly important, but so too is addressing, and actually addressing is part of IPv4. You know, I used to think that addressing was sort of cut and dry and maybe even a little bit boring, but I've learned that addressing has a lot to do with relationships between ISPs, having to do with administrative boundaries, technical issues as small and local as what happens inside a routing table lookup in hardware, to as global a set of concerns as how global addressing and forwarding is done. So it turns out addressing is really important and also pretty interesting. In the second part, we're going to cover what's known as network address translation, NAT, and a new version of IP known as IPv6. So I think you'll find this interesting. Stay tuned. So let's start with a big picture view of the Internet's network layer. Remember, we learned earlier about the network layer's control and data plane and the forwarding table. That's the router local table that determines the output port to which a router will forward an incoming datagram. And we also learned in the introduction to the network layer that the forwarding table's contents determined either by distributed routing protocols or by a router external SDN controller. We'll cover routing algorithms and SDN controllers when we study the network layer's control plane. A key part of the Internet's network layer is, of course, the IP protocol, the celebrated IP protocol. But what exactly is the IP protocol? Well, by looking at this diagram, you can see that the IP protocol is not about routing algorithms or SDN controllers. Those are control plane functions. Instead, the IP protocol is about the datagram format. It's about how IP addresses are structured and interpreted, and it's about packet handling conventions, like how to fragment large packets into smaller packets. So IP is really just a piece, albeit a really important piece, of the Internet's network layer. The ICMP protocol, which we'll cover as part of the network layer control plane, is also part of the network layer. Since the IP protocol is about datagram formats, addressing, and packet handling conventions, let's then start our study of IP by looking at the IP datagram format. Using this figure, we'll walk through the fields of the IP datagram. Now, I know this might seem a little bit dry, but really, anyone who takes a networking course really needs to know this. Sort of like eating your vegetables, you know, it's good for you, and so you really do have to do it, and hopefully you'll even love it or find it interesting anyway. Well, first, there's the version number field. These 4 bits specify the IP protocol version of the datagram. Here, of course, we're looking at the IPv4 header. Because an IPv4 datagram can contain a variable number of options, which we see here in the datagram header, the header length field indicates how many bytes are in the header. This lets the host or router know where the payload actually begins in the IP datagram. Most IP datagrams don't contain options, so the typical IP datagram header goes from here to here, a 20-byte header. The datagram length field indicates the total number of bytes in the IP datagram header plus payload. This is needed because the payload can also be a variable size. Since this field's 16 bits long, the theoretical maximum size of an IP datagram is 64K bytes, but datagrams are usually no larger than 1500 bytes, which allows a datagram to fit nicely inside the payload field of a maximally sized Ethernet link layer frame. The type of service bits were included in the IPv4 header to allow different types of datagrams to be distinguished from each other. The definition and use of these bits has really evolved over time. For our purposes, the most important type of service bits are the 2 bits used for explicit congestion notification, ECN. And remember, that's a topic we studied in detail in the transport layer. A router sets these 2 bits to indicate congestion. The remaining 6 type of service bits are used to differentiate among different classes of traffic, which can then be given different service based on their traffic class, using the buffering and scheduling algorithms we just studied in the previous section. The TTL field is a counter that's decremented by 1 each time a datagram passes through a router. If the TTL count ever reaches 0, the datagram must be dropped at the router, and so the TTL field is used to ensure that packets don't loop forever or even for a long time if there are forwarding loops. The upper layer protocol field indicates the transport layer protocol to which the payload in this IP datagram is going to be passed. For example, a value of 6 indicates that this datagram contains a TCP segment that will be passed up to TCP. A value of 17 indicates that the payload is a UDP segment. The IP ID field, flags, and fragment offset field are used when a single large IP datagram is fragmented into multiple smaller datagrams. This doesn't happen often, and actually these fields don't even show up in IP version 6, and so we won't say anything more about them here. You can read about them more by following the pointers in our textbook. The header checksum is an internet checksum computed over the contents of the IP header. Remember, we studied the internet checksum earlier. And note that since some of the IP header fields change each time a datagram passes through a router, the TTL field's decremented, for example, the checksum needs to be recomputed at each router that the datagram passes through. That can be time-consuming, and maybe as a result of this, the header checksum field was also removed in IPv6. We've already talked about the 32-bit source and destination IP address fields. Remember that we just saw in destination-based forwarding that an IP router uses the datagram's destination IP address here to look up the appropriate router output port to which the datagram should be forwarded. And then finally, there are a number of optional fields in the datagram header. We'll skip those here. And then, of course, the datagram's payload itself. The payload's the data, a transport layer segment that IP will deliver up to the transport layer protocol. Whoa. Well, that was a lot of fields to think about and to go through. And as we've mentioned, IPv6 is a lot more streamlined than IPv4, and so we'll find fewer header fields there. Let's start our discussion of IP addressing with a few basic concepts. The first important thing to know is that an IP address does not identify a host or a router per se, but rather an interface, a link layer interface on a host or router. Routers pretty much always have more than one interface, that is to say, multiple incoming and outgoing links, and hosts often do as well. For example, my laptop has a wired Ethernet interface and a wireless 802.11 interface, each with a different IP address. As we've seen, 32-bit IP addresses are written in so-called dotted decimal notation, with each decimal number corresponding to an 8-bit byte in the address field. Here, the 32-bit binary address is 223.1.1.1 in dotted decimal notation. Well, looking at this diagram, it might be a little bit unsatisfying to you. It looks like the link layer interfaces, these black lines, just sort of vaguely end up in a blue cloud. What's up with that? How are these interfaces actually connected together so that one interface can communicate directly with another interface that's attached to the same blue cloud? Well, remember that we're at the network layer right now, and the connection of these interfaces is done via link layer technologies, which are the layer below what we're studying right now. So one answer to your question would be, well, be patient, we'll get to that. But if you're just dying to see what the complete picture looks like, here's what it is. The host and the router interfaces might be connected through wired Ethernet switches, or they might be connected through an 802.11 wireless network. But there will be a link layer, local area network, or point-to-point link protocol, typically Ethernet or Wi-Fi in practice, that will be used to connect the interfaces. And we really will learn about this just a bit later. So stay tuned, and for now, back to the network layer. If you take a close look at this figure, in particular the IP addresses in this figure, you'll notice that the interfaces that are connected to each other have similar but not identical IP addresses. That's because they all belong to the same subnet. So what is a subnet? Well, each subnet is a piece of the network that contains all devices that can reach each other without passing through an intervening layer 3, that is to say network layer router. That is, they're directly connected to each other via some link layer technology. And here's how that ties into addressing. An IP address has two parts, a subnet part and a host part. And if two interfaces are on the same subnet, their IP addresses must have a common subnet part. And of course, they'll have different host parts. So let's be very specific in defining subnets. To find a subnet, detach each interface from its host or router, as we've done here, and this will leave islands of isolated networks. And so in this example here, we have 3 subnets. Now let's look at the addressing. Remember that interfaces on the same subnet will have the same subnet part of their IP addresses. The so-called subnet mask says how many high-order bits they have in common. Let's assume that's 24 bits. In this case, this lower subnet here has a 24-bit address of 223.1.3. We say 223.1.3/24, and these 3 interfaces have addresses that all start with 223.1.3. The next subnet is 223.1.1/24. Note that these 4 interfaces have addresses that start with 223.1.1, and this third subnet address is 223.1.2/24. Let's take a look at this network with 3 routers and 7 hosts. Can you find the subnets? Think about it. Well, let's disconnect the interfaces from their host or router to see the subnets. And here are the /24 subnet addresses. This slash notation that we've been using has a name. It's called Classless Interdomain Routing, CIDR, and actually pronounced CIDR due to its historical origins. The subnet portion of the address can be any number of bits X, and a CIDRized address is one of the form A.B.C.D/X, where X is the number of bits in the subnet address, and sometimes the D is omitted when it's 0. Here's an example of a 32-bit IP address and its CIDRized dotted decimal notation. Well, let's wrap up our discussion of IPv4 and addressing by posing a question that maybe you've been wondering about. How does one actually get an IP address in the first place? And really that's 2 questions. How does a host get an address within the subnet range associated with the subnet that it's going to be joining? And then sort of the bigger picture question, how does a subnetwork get a range of addresses that are going to be used by devices, by interfaces within that subnetwork? Let's look at both of these questions. Well, let's start with the first question. How does a host get an IP address for its interface? Well, back in the day, a sysadmin used to actually manually edit the IP address into a file on that host. But we've progressed a lot since then using a plug-and-play, or what's sometimes known as a zero-conf, zero-configuration approach. That's to say, an approach that uses a protocol between a host and a server rather than manual configuration to get an IP address. The need for a zero-conf approach is hopefully obvious, with billions of hosts worldwide, more than half being mobile, and these are hosts that are constantly attaching to a network and then later detaching and then attaching over and over again. The protocol used by a host to get an IP address on a network is known as DHCP, the Dynamic Host Configuration Protocol. In order to allocate a plug-and-play IP address using DHCP, a network will need to have a DHCP server to perform that function, and an arriving client, that is, a host wanting an IP address, will request and receive an IP address from the DHCP server using the DHCP protocol. When a host leaves the network, it'll give up its IP address, which can then later be reused by another host or reclaimed or maybe renewed by this host at a later point in time. We're going to take a look at 4 DHCP messages that we'll want to study. There are more, but these are really the key ones: discover, offer, request, and acknowledgement. Let's see how DHCP works. Here's the scenario we'll look at using the simple network that we've seen before. And in this network, we see the DHCP server here. Well, typically a DHCP server would be co-located in a router and serving all of the subnets to which that router is attached, but we've shown it here as a separate server, which also happens with an IP address of 223.1.2.5. And here's the arriving client that will want an IP address in the 223.1.2/24 subnet. Now let's take a look at what the DHCP client-server message exchange actually looks like. In the first step, the arriving client broadcasts a DHCP message that will be received on the interfaces of all of the hosts and routers in the subnet to which it's attaching. The discover message basically says, hey, is there a DHCP server out there? This is a form of service discovery. The host knows the service it needs, DHCP, so it sends out a broadcast to discover the server that can provide DHCP service. DHCP runs over UDP, the client uses port 68, and the server will use port 67. In particular, the server will be listening on a socket associated with UDP port 67 for incoming DHCP messages. And here are the details of the fields in the DHCP discover message. The client's source IP address containing the UDP segment that contains the DHCP discover message is 0 because the client doesn't have an IP address yet. And the destination IP address is the IP broadcast address, that is all ones, 255.255.255.255. And the UDP destination port number is 67, as we just noted before. Hopefully, there'll be a DHCP server sitting out there somewhere on the subnet listening for this service discovery message. Note also that there's a transaction ID field. It's got a value 654 here, and this will be used by the client to match any reply to this request. Here's the second step. Any DHCP server that receives this broadcast discover message, and there might be several such servers, can reply with a DHCP offer message. This message basically says, hey, I'm a DHCP server and here's an IP address that you can use. If we look at the details of this offer message, we see that it comes from the DHCP server with an IP address of 223.1.2.5, as in our figure earlier, and from port number 67. This offer message is being broadcast to all interfaces on the subnet. The DHCP message contains the IP address that the requesting host can use. That's the YIADDR, your internet address field, and a lifetime, in this case, of 3,600 seconds that the address can be used for. Note that the transaction ID here matches the transaction ID of the initial offer message. That's to say, this is a reply to that message. A client can receive offers from multiple DHCP servers, and this might occur, for example, if there are multiple routers on that subnet. Now, the first two steps that we've seen here are actually optional. The way to think of the third step, which could also be the first step if the two optional steps aren't taken, is that the arriving client comes in and says, hey, here's an IP address that I want to use. Maybe that's the IP address that it was told it could use in step 2, if that step was executed, or maybe it's an address that it already has, in which case the client is really renewing its use of that address, or perhaps it's an address that the client's used before. You can see here that this message is also broadcast and that it contains the IP address that the host is proposing to use, and that there's a new transaction ID and a lifetime as well. The final message is the ACK message from the DHCP server saying basically, okay, you can use that IP address with this given lifetime. Now it turns out that a host needs more configuration parameters than just an IP address in order to be able to function. In particular, it also needs to know the IP address of the first hop router, since any outgoing packet from the client will need to be sent to that first hop router. It might also need the address of a DNS server to use, and also need the net mask, the number of bits in its IP address belonging to the subnet. Well, this could all be configured manually, but it can also be optionally specified in a DHCP message, and this is usually the case. So the other really big question that we still need to ask is, how does a network get a range of addresses to assign to the devices, actually to the device interfaces, in its network? Well, in many cases, it will be allocated a range of addresses in the IP address range that belongs to the ISP to which it is a customer network. In this example here, the higher level ISP has a /20 address range. This ISP could then, for example, divide its address space up into 8, say /23 address ranges, as shown here, and allocate each of these out to one of its 8 client networks. And now we can start to see a really critical tie between addressing and routing, something that we'll come back to again when we get to the network layer control plane. In this example, the parent ISP, which we'll call fly-by-night ISP in this example, has 8 client ISPs. As shown in the figure here, fly-by-night need only advertise one address prefix, 200.23.16/20, to the rest of the global internet. This single advertised address prefix will be sufficient for the rest of the internet to be able to route to the 2 to the 12th addresses in this ISP's address range. This is an example of what's called address aggregation, sometimes also called route aggregation or route summarization. Note that in this figure, the second ISP, let's call it ISPs are us, says, hey, send me anything in the address range 199.31/16. We'll come back to this in just a second. Well, this all looks very neat and orderly, but in life, well, things just generally aren't so neat or ever so perfectly hierarchical. In particular, let's ask ourselves, what would happen hypothetically if one of the 8 client ISPs, say organization 1, wants to change ISPs from fly-by-night to ISPs are us, while keeping its range of network addresses 200.23.18/23. Well, fly-by-night continues to say, send me anything with address prefix 200.23.16/20 as before, and as we can see here. But here's the critical thing. Now ISPs are us says, well, send me anything with address range 199.31/16 as before, but now it also says, also send me anything with address range 200.23.18/23. And note the /23 here, and note that 200.23.18/23 is contained in fly-by-night's advertised 200.23.16/20 address range. So, what are we to do here? Well, what's absolutely critical here is that ISPs are us has advertised a longer 23-bit prefix 200.23.18/23, a more specific prefix than the 20-bit prefix 200.23/16/20 advertised by fly-by-night. And I hope oh yeah, light bulb has just gone off in your head. Remember when we were studying forward tables, when we were looking at what's inside a router? When looking up a 32-bit IP address, the matching forwarding table entry is that with the longest prefix match. That's precisely why packets with addresses in organization 1's address range will be forwarded to ISPs are us, which has advertised the longer prefix. Well, we've now seen how address allocation, forwarding table lookup using longest prefix matching, and the BGP routing protocol that disseminates prefixes are all really intimately tied together. And if you've got all of this, you've really mastered and tied together a lot of key concepts. If it's still not 100% clear, we'll come back to this again when we study the control plane, but maybe think a little bit more about it now if you don't have it quite down. So we've now seen how a host gets an IP address from a DHCP server, and we've seen how customer ISPs can get an address range from their provider ISP. But we still haven't answered the basic question at the highest level: how does an ISP get a block of addresses? And the answer to this final question is that the IPv4 address space is owned, administered, and allocated by an entity known as the Internet Corporation for Assigned Names and Numbers, ICANN. ICANN in turn allocates addresses out to 5 regional registries, which then allocate out their portions of the address space to ISPs. ICANN also performs a number of other critical internet functions like managing the root DNS servers, managing domain names, and allocating protocol numbers. Remember when we studied the IPv4 datagram format and said that the upper layer protocol number of 6 corresponds to TCP and that the number 17 corresponds to UDP? Those numbers are also controlled by ICANN. Well, let's wrap up here by considering IPv4's 32-bit address space. In 2011, ICANN Central allocated out the last of its available chunks of 32-bit address space to the regional registries. ICANN has no more address space to allocate out, although there's some unused address space still sitting in the regional registries. In the next section, we'll look at network address translation, a technique that allows a single IP address to be used by multiple IP devices, and we'll also look at IP version 6, which has a much larger 128-bit address space. IPv6 was begun in the 1990s specifically because the IETF foresaw the exhaustion of the IPv4 address space. Well, you see this quote here from Vint Cerf, who along with Bob Kahn we can really credit as being one of the two founding fathers of the internet if we had to choose just two. They've both been asked a lot about the early days of the experimental ARPANET that later grew into today's internet, and about the 32-bit IPv4 address space in particular. And I love this quote from Vint. Who the hell knew how much address space we needed? Remember, when today's internet architecture was being defined in the 1970s, it was a relatively small Department of Defense project. So let's leave the last words here to be from Vint Cerf. I heard him give a really great sort of fireside chat type of talk at Georgetown University in 2017 when I was working in DC. And he talked about a lot of really interesting topics, but one of them had to do with IP's 32-bit address space. So let's hear it from Vint. How did we actually end up with a 32-bit address space? What calculations did they go through? Take a look.
So now we have 4 different kinds of networks: the Ethernet, the packet radio net, the packet satellite net, and the ARPANET, the original ARPANET. So we sat down and tried to figure out how are we going to do that, and after about 6 months we had designed the basic protocols that you use today. It was just TCP. Later on we split off the internet protocol for real-time communication. So the question then was, how big did we expect this to be? Well, honestly, we sat down and said, this is going to be used by the Defense Department. It has to work everywhere in the world because you never know where the Defense Department is going to have to operate. So we said, okay, how big is this going to be? It's got to be global. How many networks will there be per country? And we said, well, we had finished the ARPANET, which is a non-trivial national scale network. So we thought, well, maybe there'll be 2 per country. So there'll be some competition. So we said, okay, 2. And how many countries are there? And there wasn't any Google to ask back then. So we guessed at 128 because that's a power of 2, and that's what programmers think in. So 2 times 128 is 256 networks, and that's 8 bits of identifier. And then we said, how many computers will there be per network? And we said, remember, this is 1973. These are giant air-conditioned computers, that serve 1,000 people in time-shared mode. So we're saying, how about 16 million? What the heck? So 16 million is 24 bits. So we ended up with a 32-bit address space, and if you do the math, it's 4.3 billion possible terminations for the network in 1973. So the answer, that was more than there were people in the world at the time, I think. So we thought, well, that ought to be enough to do this experiment, right? So that's what we used. So people say, if you had it to do over again, what would you do? And one answer is, well, I guess I would have chosen the 128-bit address space so we don't have to go through this painful transition. On the other hand, can you imagine making an argument of the form, I need 3.4 times 10 to the 38th addresses in order to do this experiment. How many networks do you have now? 3. How many computers do you have on the networks? 500. He said, something doesn't quite add up, does it? So I didn't do it because it wouldn't pass the red face test. But I wish I could have.